Good morning, everybody. I hope you can hear me, and I would like to welcome everybody to our session. This day, the DYNAmore Express webinar session. And in this session, basically, it's the second part. Again, it will be given by Dirk Dreißig from LASSO Engineering. Dirk studied at the University of Stuttgart, and now he's working for LASSO Engineering. And part of his job is also doing the customer support for Unser and META post. Today he will give the second part of his talk, and today it's related to how to couple Unser and META post with LSOpt during the optimization. And with that being said, I'm going to hand over to Dirk and enjoy the sessions. By the way, before we start, just a few comments. At the end of the session, we will again distribute some feedback form. Please fill it out. And also, if you have questions, post them in the chat, and we got trying to answer the questions after the session. Okay, so just post the questions in the chat, and then afterwards we're trying to answer as many questions as possible. Okay, and now it's time to hand over to Dirk. Dirk, you just share your screen.
Yes, I will do so.
Okay.
I share the whole screen this time, not only the presentation, because I want to show something in Unser as well.
Okay, I can see it.
Yeah. Okay.
Perfect.
So then let's start. Morning, everybody, from my side as well. Today, second part of our optimization with Unser, LSOpt, and META session. Last week we saw the possibilities of Unser for parameterization of RFE models, which is the prerequisite for doing an optimization. And today we want to have a look on how to connect Unser and META to LSOpt. So the first question is for what do we need actually Unser and META when we do optimization with LSOpt? Well, you need Unser in order to change your model in shape according to some given design variables. When you only have parameters in a text file, an input file, this actually can be handled directly from LSOpt. But if you want to do some morphing, for example, you need an external tool for doing that. So that's why we use Unser here. And similar for META, if you have result files only in text format, you can directly use, or LSDyna results, you can directly use LSOpt and the features from it to extract the required results. When we use other solvers like Abacus or any safety solver, we need a tool to extract the results from the result files of the solver and maybe create some curves and get some maxima and so on. So that's why we use META for the result extraction. The process, which software transfers which data to which other software is a little bit different in the phase when we set up the optimization. So in this setup phase, we usually use Unser to define our design variables. And then these design variables are transferred to LSOpt. So we don't have to define them twice in LSOpt and in Unser. So we do it in Unser first and then transfer it to LSOpt. And the same for the histories and responses that are required for the optimization. We define them in META, and after that, transfer them to LSOpt. In the actual run mode, when the optimization really runs later on, it's the way of the information is a little bit different. So we have LSOpt controlling the whole optimization. The design variables are controlled from LSOpt, are transferred to Unser, and Unser adapts the model accordingly. And META calculates the histories and responses as they are defined in the setup phase, and then transfers the values to LSOpt. And we will have a look now on these two parts in Unser and in META. How do we set up there the optimization? So first, we want to have a look on this whole setup phase the diagram, what we do in which sequence. Well, we always start with Unser and with an Unser database of our model that we want to optimize. Actually, the part we treat in Unser must not necessarily be the whole FE model which is to be solved. If you have a large model and only a part of it undergoes some optimization, it's more efficient to do only this part in Unser, do the morphing on it, and then include it in the whole FE model by some include statements if the solver supports includes. So the morphing stuff will run much faster, of course, if less elements are involved. So in Unser, the main interface for optimization is the so-called optimization task. In previous versions, of the optimization task was a part of the task manager. Actually, it's still a part of the task manager, but since some versions we have a special tool for optimization. It's called the optimization tool, and we will use this from now on. The task is part of the optimization tool, and in the optimization task, we define our so-called DV file, design variables file. It's actually a text file which contains all the design variables. We define our design variables themselves, and the solver input deck, which is created at the end of the optimization task. And we need to link our design variables to our model parameters. So a design variable actually is only a vehicle which transfers the values of the design variables to our model parameters. We can link design variables to morphing parameters, Unser parameters, and user scripts. We will see in a few minutes how to do that. So when we have set up our optimization task, we will run it once in a so-called baseline run. This is actually for validation of the optimization task to see if everything runs smoothly, if there's no error in the task, we don't have any errors in the model at the end of the task, and it will output the solver file at the end. Furthermore, we need to save this design variable file. For those of you who are a little bit familiar with optimization task, maybe you remember that we had a so-called definition mode in the optimization task and execution mode. And whenever you switched from definition mode to execution mode, this design variable file would be solved. This is not necessary anymore. So these two modes, definition and execution mode, do not exist anymore. So we can just define our task and then run it. And in order to save the design variables file, we can simply right-click on it and say save. So it's much more intuitive. When these files have been saved, we actually have a ready to run solver input, and we can run the solver once to check well, if the solver runs at all, if no information are missing, especially if we work with includes, make sure that we don't have any missing materials or something like that. And we get a sample set of results with which we use in the next step for defining the result extraction procedure. So we move on to META. We load there the solver results. For example, if we have a Nastran run, we load the OP2 file and do our post-processing, search for the maximum stress or whatever we want to evaluate. And we use typically the so-called optimizer setup toolbar in META. And for those of you who are familiar with META, META is actually command driven. So everything that you do is recorded in the so-called session file. And we can run this session afterwards to reproduce the result of the post-processing. So this session file is actually similar to what we execute in Unser with the optimization task. So in this session, will at the end output a formatted result file, similar to the design variable file from Unser. And this result file can be read, the text file, which has the responses and histories. This can be read by LSOpt. We can go with the DV file and this meta result file into LSOpt. That's the last step actually. So far we have nothing done with LSOpt. We only used Unser, the solver and meta. So the last step is when we have all the information together, design variable file, the histories and responses in this meta result file. We run LSOpt. We input the design variables from Unser from this design variable files. We input the histories and responses from meta and further set up our optimization. So introduce some dependencies in the design variables, some ranges, specify the optimization strategy, and define our objectives and constraints for the optimization. All right, so that's the workflow of the setup. And we will now have a closer look on the different steps in Unser and META. And we start with Unser and the optimization task. So as mentioned, we use the optimization tool. In the workflow tab, we have the optimization task, or if we don't have it, we can create it just with right click. And this optimization task consists mainly of 3 so-called task items. The first one is the definition of this design variable file. Then the design variables themselves. You can have as many as you need, as you require. And as third, the output task item for the solver input file. You can have some more, we will see it in some examples, but these 3 are mandatory. Let's have a look on the design variable file task item. As mentioned, it's a text file which contains, when it is saved, all the design variables that are defined in the task with their properties like their minimum and maximum value, current values, what type, which range they have. And this is a format syntax which is can be interpreted by LSOpt. So we can directly input this file into LSOpt and get all the design variables defined there. So let's have a look on the design variables here. We have a task item here called emboss's width. This is actually the design variable item. You open the card, when you edit it, get like the other Unser entity cards, the values, it's of type real, define some bounds. And this design variable is connected, see the child items here, with 3 morph parameters. So this is actually the interface between our design variable and our model parameters. So, and when LSOpt gives a set of new design variables, new values, the design variable changes. This changes the child items, in this case, the morphing parameter. And the morphing parameter in our case here controls the width of these depressions. So by changing the design variables, the morphing parameter changed and the model is morphed accordingly. All right. At this point, we will have a small trip to Unser. I just switch to Unser. Just for you to see how we can define the design variables. There are different ways. So at first I open here the optimization tool. This is how it looks. At the moment, we don't have any optimization tasks. So I just right click here, optimization task new. And you see these 3 items here, at least. And we have a design variable, which is not connected to any model parameter. In order to connect it, we can just right click here and say with which parameter we want to connect it. But there are some more easy ways. If we already have parameters, for example, in this case here, I already have a morph parameter. So if I want to create a design variable out of it, I can do it directly from the parameters list here, right click on it and say assign DV. If you do it on several morph parameters, you can say, okay, whether you want to create one design variable for all or separate design variables for each morph parameter. Having done this, we have here a new design variable which connects to the morph parameter. I just switch on the type here to see what each item is. There's also the other way around. When we don't have any design variable here, we can just delete them. I can right click on the parent part of the tree here on pre-processing and say I want a new design variable. For example, from parameters. And then it opens a list with all the parameters, either morph parameter or Unser parameter. I can select that and get the same result. But even if you don't have a parameter yet, for example, if you want to change or create a design variable for controlling the width of this shell property, we can create a new design variables from entities. So, and then we select here property shell section. I'm in Abacus stack at the moment. I select the section. And then it opens a list with the available fields. And if I want to change the thickness, I choose the field T, say OK. And what Unser actually does is it creates an Unser parameter here. Field T is now controlled by an Unser parameter, and this Unser parameter is connected with the design variable. So these are the ways to create design variables in Unser. And see, you can do it quite easy in one step for all morphing parameters all at once. All right, so let's switch back to our presentation. We will see here another example where the design variable is connected with such an Unser parameter. In this case, the design variable is defined a little bit different. We don't have bounds here, but we have specific steps that that this design variable can get. So can get a real value with a step width of 0.1, so either 1.6, 1.5, 1.4, but not 1.358, for example. And this design variable is connected in this case with an Unser parameter, controls the Unser parameter. And again, the design variable changes the Unser parameter, the parameter changes the card field, and this changes thickness of our profile here. Another example for using Unser parameter is in the connection manager in order to control connection lines. In this case, spot weld lines. Can have a design variable that controls a parameter for the distance between spot welds or for the diameter of spot welds. All right. So that's actually pretty much all for the optimization task, or at least for the design variables. This optimization tool has a simulate functionality. This is quite helpful for doing some or for checking combinations of design variables. For example, you can do a full factorial combination of design variables to check the model validity. If you get a valid model with any combination of design variables, or if you need to specify some constraints in the design variables. So for this, the simulate may help. And it's also good to checking the element criteria, especially if the design variables reach their limits. Here we have an example where we change some design variables, some morphing parameters, and the more we change it, the worse the element quality gets. And we can hardly use this mesh directly for the FE solver. May complain that the element quality is too bad. So we can use the simulate functionality in order to check this and then act accordingly. And for example, we can add further items to our optimization task. In particular, some small scripts which do further actions. For example, we can use a script to for improving the mesh quality. So, well, last week I said when we decide, or when we connected the design variables with the morphing parameters, we can actually, or the morphing parameter actually knows which area is morphed, and it can apply some mesh improvements directly. But if we have, like here, a lot of design variables which change more or less the same area, it does not make sense to improve the quality after each design variable item. So we would have to improve several times for the same area. So in this case, it's better to have one improvement step after the design variables. In this case, a small script. Here, a recons caliper, which in this case does a reconstruct on the affected area. All right. There are other functionalities we can add here. For example, this is actually the brake caliper here is actually a solid model, but it is more effective to do the morphing only on the shell mesh without the solids inside. It's much faster, especially if we have a lot of design variables here, a lot of morphing actions. I prefer to do the morphing on the shell mesh only, but then in order to get a solid mesh for the solver, we need to create a solid mesh afterwards. So this can also be done with a small script at the end. So we have here create volume and mesh it. That creates the volume mesh, and if this is only a part of a whole model, we need to have an eye on the number ring of the elements and nodes in order not to get any conflicts with the rest of the model. So you can even add the small script for doing a renumbering. Okay, at this point I will again switch to Unser and show you another example where we use scripts. Back to Unser, I have to open the file. So here we have a stabilizer, and you see some cylindrical morphing boxes by which we control the diameter here of this part. And okay, we can increase the diameter here. I can show you how it looks like. First, I will just cut some elements out here, and you see the thickness throughout the whole pipe is the same. And when we toggle some things here. Since I don't want to use it for an optimization now, just to run the task. I change the current value here to some different values. Currently, the current value is 0, and if we increase it, I would expect here an increased diameter. So I run the task in order to apply these values. You see what happens. The diameter is increased. And now we wanted to keep the material the same. So like when we do a hydroforming, when we increase the diameter, actually the thickness in the higher diameters decreases. So we thought, how could we do it in the optimization task? Just do an undo. And for this, we use a small script. Actually, you see here that this area is separated in several properties. And each ring can be controlled, for example, by scripting. So I activate here these two script items. And now I let it run again. So the result looks pretty much the same, except that here in this area where the diameter is increased, the thickness is decreased. So in each ring of elements, we have the same material as before. So that's just another example of using scripts in the design, in the optimization task. Just to give you an idea what can be done. All right, so let's switch back to our presentation and continue with META. So let's assume we have a ready-to-run solver. We have run the solver and got some solver results. And in META, we use the optimizer setup toolbar in order to create the responses and histories required for LSOpt. So we do our normal post-processing work, even if we have some automated process like some scripts or session files existing already. We can just run them. And how can we connect values of META? How can we say that these is a response and this value is in history? Actually, we can use or we can create responses from either annotations or from some variables that we define, or even some advanced expressions, some formulas. So the easiest way is to do it with an annotation. So the value you want to have as response, just create an annotation on it, either in the 3D model, maximum stress of the whole part, or in a curve, the maximum acceleration in this case over time. here the maximum x coordinate for another response. So you just add them with the optimizer setup toolbar. You pick the annotations and you get the responses. If you need to define some histories, you directly use the 2D curves from META. And at the end, you use this export session button, and META will create or will save the session file up to this point in order to reproduce everything that we have done in order to extract the results and the responses. And it will output the so-called META result file. It looks similar to the design variables file. And again, this has correct syntax to be directly imported in LSOpt. All right, so these were Unser META steps. Now we see how to use Unser and META in LSOpt directly. We have a separate stage for Unser. We can create a new stage and say in the package name it's Unser. All we have to specify is the command to run Unser. I want to emphasize here this -lm retry option, especially if you are not the only one who use Unser. It may happen that when LSOpt calls Unser, maybe no license is free. And it's really bad if the whole optimization stops just because the license is temporarily not available. So we tell Unser with a -lm retry that it should retry after 10 seconds in order to get a free license. All right, what else should we define? Here, the design variable file that was created from the optimization task. And of course, the Unser file with the model and the optimization task. So Unser outputs the design variable files. This design variable file is read by LSOpt, and we have all the design variables with the defined parameters inside LSOpt. Then we can further adjust the design variables, for example, specify some initial ranges or some dependencies or whatever. Maybe we want to deactivate temporarily some design variables. All this is done directly in LSOpt then. For META, it's pretty much the same. We, after the solver has run here, we have a META stage. Again, we specify the META command with the lm retry function option. We give the session file that was created from by our optimizer setup toolbar and this output file. From the output file, LSOpt reads the responses and the histories if they exist. And then we can further set up our objectives and constraints by using these responses. All right. That's pretty much all for that's important for the setup of the optimization. We will quickly go through the workflow, what happens when the optimization actually runs? Well, the whole optimization is controlled from LSOpt. LSOpt will, in each iteration, produce a design variable file with specific values of the design variables. For example, here, one width of this area controlled by design variable number 6. And LSOpt will call Unser. Unser will read the current values of the design variables and adjusts the design variables in the optimization tasks accordingly. So it will change the current value like we did manually before. And then the task is executed in sequence from top to bottom. And this is important because the sequence of the design variables controls how, in which sequence the model is morphed. If you remember last week when we spoke about box-in-box morphing, I said that it is important that the auto morphing is done before the inner morphing. So in order to control this, you just need to make sure that the outer morph parameter is first morphed. The design variable that controls the auto morphing is specified before, above the design variable that controls the inner morphing. So the sequence is of importance. And at the end, the task will output the solver input file. And if this is done, Unser closes. Actually, Unser will run in batch mode. You will not have an Unser window pop up open. It will completely run in the background in batch mode. So if Unser terminates normally, LSOpt is notified and LSOpt will run the solver afterwards. So the input goes into the solver produces some result files, and if the solver is finished, LSOpt will call META in order to do the result extraction. So with our solver results, we go into META. Again, META is run in batch mode typically, and META will execute or will produce the response file, so the META results file. These are read by LSOpt turn. LSOpt will evaluate the objectives and constraints, and then for the next loop will produce a new set of design variables. And this whole process is repeated until the optimal solution is found or the maximum number of iterations is reached. Well, that's all. Thank you very much for attending. And if you need more information on LSOpt, please visit lsoptsupport.com. There are also some examples concerning the coupling of Unser and META, some tutorial files. But of course, you can also contact us directly if you have a particular question for a project or something similar. Thanks again for attending. And yeah, do we have some questions?
Okay, thank you, Dirk. I just checked. At the moment, there are no questions in the chat. So maybe someone is coming up with some questions. He has to type it. So I will already post the link to the webinar evaluation in the chat. And again, feel free to evaluate this session. So yeah, I will just share my screen again, the final slide. And yeah, so there's no question coming. So with that being said, evaluate the session. I hope you enjoyed it, and see you next week on Friday at 9 a.m. Yeah, see you next time, and goodbye, everybody.
Goodbye from my side as well.